From MCJ, I'm Cody Sims, and this is MCJ's Startup Series. Today, our guest is Doug Bernauer, CEO and co-founder of Radiant. Radiant is developing a portable nuclear micro-reactor to replace diesel generators. They raised a $40 million Series B in 2023, led by A16Z, after previously raising capital from investors including USV, Founders Fund, and DCVC. They're targeting development of a portable, mostly self-contained 1-megawatt nuclear reactor that is roughly the size of a shipping container. As regular listeners will note, I've been spending an increasing amount of time on nuclear, primarily trying to understand whether it's realistic to expect that the U.S. will reestablish itself as a global innovation leader in the space. Recent legislation signed into law by President Biden, such as the ADVANCE Act, show that there is bipartisan support for this, a rare thing in today's political environment, and there are signals of change in the wind, but it's still likely a long, challenging road ahead. I was interested to hear from Doug about how he views this challenge, how Radiant works, the use cases it's targeting, the fuel it uses, and much more. But before we start, I'm Cody Sims.
I'm Yin Liu.
And I'm Jason Jacobs, and welcome to My Climate Journey.
This show is a growing body of knowledge focused on climate change and potential solutions.
In this podcast, we traverse disciplines, industries, and opinions to better understand and make sense of the formidable problem of climate change and all the ways people like you and I can help. Doug, welcome to the show.
Hey, great to be here, Cody.
I've somehow accidentally been on like an LA tour lately of startups, so fun to talk to another entrepreneur working out of LA on an important clean energy technology.
Yeah. Should I describe who I am, what we're doing here?
Oh, we'll get there.
I want to hear about your tour. I don't know about this.
Oh, yeah. Well, it was accidental. So I'm trying to even think who we've had on now. We've had a hydrogen startup on recently, and now I'm totally botching this setup because I forgot who the other ones were, but
yeah,
there's a bunch of stuff going on in LA.
All right. Well, next time you do a tour, you should come by here.
Well, a physical tour would be really cool. I'd love to see what you guys are doing. Why don't we start by having you describe that? So describe what the Radiant reactor looks like.
Yeah. So what we're developing is a portable micro-reactor. It's a container that has a reactor, shielding, a helium loop, and then a spinning turbine in it that generates electricity. And the idea really is that you could use a 1-megawatt nuclear gen set instead of a diesel gen set, and use that for prime power or for backup power or at a construction site. There's a whole bunch of applications, and you can operate this for years without refueling. Whereas if you've got a diesel generator, you've got to move about 5,000 gallons of fuel every couple of days to that site per megawatt.
And so when I talk to different companies working on different new reactor solutions, a lot of companies I talk with are like, oh, we're starting with this 1-megawatt test reactor, and then we'll then have a 10-megawatt reactor, and we're eventually going to get up to 100 or a 300-megawatt sort of SMR, if you will. But it sounds like your goal is, no, we are trying to build micro-reactors. Like that is our product. Is that correct?
Yeah, actually, build at 1 megawatt, mass produce at 1 megawatt, and then go even smaller. So I'm actually looking the other direction.
What are the primary use cases that a 1-megawatt reactor can solve? Like maybe give me a sense of the order of magnitude, the order of scale. Are we talking a neighborhood block? Are we talking off-grid industrial site? Like what are you looking to solve for?
Yeah, great question. So best way to get scale on it is you can power about 1,000 homes in the US with about 1 megawatt. So that's the scale for one unit. We look at configurations of from 1 to 4 of our units. So kind of 1 to 4 units makes a lot of sense for customers. I think we can beat a lot of other options in nuclear. Eventually, you probably want to be using something bigger if you've got the time to go and construct it and put it down a hole and do some downhole fission. Our reactor is above ground, and it's meant to really not have infrastructure requirement. So that's the sense of scale. But some of the use cases would be when you're using nuclear power to save lives. So you have this ability to take a box and set it down and have it up and running in a day. You could use that for disaster relief, which today you're reliant on turbines, either natural gas or diesel-fueled turbines that you've got to go set up that are then going to chug out a bunch of fumes, some carcinogenic fumes and some CO2 in an area. And so that's really the super interesting thing you can do at a 1 megawatt scale that you can't do at any larger scale of reactor.
Let me ask a question on that, which would be, I would think for disaster relief as a use case, I'm guessing a nuclear reactor is going to be a lot more expensive up front than a bunch of diesel generators, which may be more expensive to operate over time because you're constantly buying fuel for them. But if you're dealing with disaster relief, isn't that upfront expense going to be somewhat prohibitive?
Yeah, I mean, disaster relief is not really the earliest market that we'd be getting into. I think the most interesting customer cares about resilience of power. If you want to take that disaster relief point, it totally makes sense that if you didn't want to move diesel every couple of days to that site and you just want to turn it on, focus your attention not on trying to keep a thing running, like pulling fuel in and chugging fumes out in that local region, that's really all it would do for you. I just think it's really interesting, really exciting to think about how can you use nuclear power to save lives. So if you add resilience to a hospital that is grid reliant, they have diesel generators today because, right, there are life support machines that if they go out, then people's lives are on the line. There's other compounding factors too. So I'm in California, so wildfires are very top of mind, right? And power companies are shutting off power to lower those wildfire risks. So this means that anyone who wants to keep operating, you need to have solar and batteries and wind and maybe some nuclear, especially if it's night or if those same wildfires block out the sun for your solar panel. I think it's an interesting option to be added into the energy mix. And at a megawatt, it's extremely nimble and can fit in these niche markets. So disaster relief is actually being studied at federal level, the use of it for disaster relief. But the primary benefit there is to not pollute. It's a completely green way to do disaster relief, which I think is wild.
And describe your reactor. As I've seen on your website, you mentioned you don't have to dig it into the ground. You don't have to create cement. Like, it's essentially a shipping container that you can put on a truck and move around.
It's a little bit more complicated. It is a shipping container you can move around on a truck. The very cool thing about that is it's the nuclear power that people want. And the point there is you use up nuclear fuel. It's not all gone. You create a bunch of fission products. Those stay inside of our unit. But we can shut off the unit, wait about 30 days, and then put it on a truck and take it away. And that's the model for all of them. So you can get clean power. You can get it over a weekend, nearly immediately, right? And then you don't have to sign up your site to have nuclear waste on site, which is the case for any category of reactor larger, for larger micro-reactors than 1 megawatt included. But we do plan to put concrete around units as extra additional shielding. And the reason is you can put about 4 megawatts on a tennis court of space if you put some concrete up around it. And there are more customers for that sort of model. And we have some promotional materials that have been released showing some of that. The website is just a little outdated. They sort of indefinitely are, right? The website is, it's either you can buy units there or it's just a business card. And for us, it's a business card. You can't pre-order reactors yet, but we need to update it. And one of the things I want to update is that how it exactly looks at the customer site. We really just show it being transported.
And you mentioned that the fuel doesn't get stored at the customer site. So that are the units then taken back to some central location for fuel refilling?
Yep, that's exactly right. So we are developing a factory. We are looking at a whole bunch of customer sites. We want to select site actually by the end of this year. So we've gone through, I think, 14 states we've had direct interactions with, gone to visit about half of those, and we've dropped the list down to 4 remaining. But what we'll do is set up a factory there where we can refuel units. We'll have 2 refueling cells. So you'll have a unit arrive, go into a refueling cell. There's a robotic system that will open up the shield, and then the reactor pressure vessel put tooling down inside of the graphite core block and then pull the graphite out with all the fuel in it and transfer that to a dry cask. And then we have dry cask storage. So on the really big reactors, usually fuel goes into a big pool and sits underwater to cool for a long time. Because we have a ceramic fuel form, it doesn't have to cool significantly, and there's a really small amount of it. And we do wait about 30 days before shipping it. So we cool prior to shipping and then are able to go direct to dry cask.
Okay. Yeah, I'm going to spend a bunch of time talking about your fueling infrastructure because I know that's been an interesting consideration, particularly for smaller reactors. But just to make sure I understand the customer use case here, if my hospital is depending on this 1 megawatt reactor, and then every few years it needs to go away to get refueled, like, do I have a backup diesel system I'm using in the short term while the reactor is gone? Is that the idea?
I think that certainly could work. I think there's a number of options, right? So I don't think anyone wants to be left with only a single option ever. Say you've got a battery system and solar power, and that's the primary way you're creating backup, right? That's maybe not as resilient in certain weather conditions, but also if you have a big change out of that battery system, well, you're going to be temporarily without. And so I think a mixture is always better. But it could be, right, you've got that, or you've got one nuclear reactor and a diesel genset, or the reliability of nuclear is proven out on our system, on Kaleidos, and you just put 2 or 3 or 4 of those units in. And then the refueling doesn't really matter if you've got 4 megawatts, you've got temporarily 3.
And then thinking about how the system itself actually operates, I believe you guys are the reactor type of a high-temp gas-cooled reactor or an HTGR. Is that correct?
That's correct.
And so as I understand it, if you think about like a big utility grade 1,000-megawatt reactor, these are typically light water reactors where you have huge kind of cooling pumps and water moving through and cooling the fuel, as you mentioned. Cooling the fuel or cooling the actual reactor core, I guess?
Yeah, fuel heats a graphite block and then helium flows across that graphite, picking up heat.
In a light water reactor?
For us, for our particular version of a high temperature gas cooled reactor. So
Yeah. In your system, you essentially don't necessarily need all these significant cooling pumps and mechanisms that, again, provide a lot of the construction cost of a typical reactor because you're using this sort of helium flow system. Is that accurate?
Well, we still pump, but certainly it's not as many things. So actually, one of the biggest challenges technically is our helium circulator. And that's because we have to operate about 50 times atmospheric pressure with our system to get sufficient heat transfer across a short distance. But a typical large system that you're talking about usually has several pumps because it is very critical that they keep flow in the reactor, right? They, by design, can melt down. A high temperature gas reactor uses a ceramic coated fuel that can handle extreme temperatures. So actually there's not a danger of the fuel melting down in the core. Our helium pump, we just have one pump for that reason. And that pump is allowed to fail. And if it does fail, we cool naturally with just natural convection. So we allow some airflow along the outside of a stainless steel pressure vessel. That's about 6 feet in diameter, relatively small. We actually posted some pictures recently people can find on LinkedIn, but it naturally cools. And that is a trick you can really only get away with at the micro-reactor scale, where you've got a small amount of fuel, you've got a large surface area compared to the volume that you're trying to cool. And so, yeah, there is a little less complexity due to that passive safety.
And this mechanism is, I think, originally based on the Pele design out of Idaho National Lab. Is that accurate?
There is a tie-in there. So I was at SpaceX for 12 years prior to starting Radiant. I was there when the Pele program got announced, which was January 2019. And I jumped up and down with excitement and chased it around and talked to people at SpaceX and wanted to do some nuclear startup within that company. And failing that, about 5 months later, I founded Radiant and jumped out and started and actually submitted a Pele proposal. But it was a fledgling Radiant back then. And, Pele was a program to get reactor designs. So initially there was no design. I did work with Idaho National Lab with particular folks there. And there are a lot of space reactor designs that I studied that came through that lab. Some of those are foundational to the design decisions that led to our Kaleidos reactor.
That's a super helpful distinction, Marie. So Pele is not like a test reactor that people are basing things off of. It was actually a big RFP.
Yeah, there were initially 3 applicants selected. There's been 2 layers of down select. So there's now one company building a reactor under that program. So you could say there's a Pele reactor now.
Got it. There we go. And then you've had a separate DOE selection recently, I guess, around fuel testing. Is that right?
Yes, a couple of things. So in total, we have about $9 million in DOE and DoD funds on these contracts. So one of them is a fuel capsule design that is designed to go into the Advanced Test Reactor, ATR, that's at Idaho National Lab. That's been there a very long time. That reactor is actually where they do testing for fuel for the Navy and for all sorts of reactor designs. So that work is really exciting because we have the best people who always design these capsules setting it up so that we can test our fuel and potentially graphite and moderator materials in the very same capsule. And there's a slot reservation. So what we can do with that is you can, in just months, get years worth of fluence on your fuel. And so that's a big advantage there. I haven't really mentioned schedule. So we are building a first reactor unit that we call the Kaleidos Demonstration Unit. And there's a separate award with Idaho National Lab called the FEED contract, which is front-end engineering and design. And so we will be able to test that unit without doing that advanced test reactor fuel capsule test. That fuel capsule test is critical for NRC licensing for our product. So those 2 things are happening in parallel.
And there was some safety design approval you recently got from the DOE, is that right?
Yeah, that's right. So there's the DOE authorization licensing process that we're following. to test our reactor on that 2026 timeline. So it's a full-scale reactor, 3.5 megawatt thermal that'll turn into 1 megawatt electric eventually when we commercialize. And we have one of the 5 steps completed in that authorization process, which is the safety and design strategy. So that went through the ringer. We spent a lot of time developing it, getting it to INL, having it reviewed there. We went back and forth, answered a ton of questions. And then that safety and design strategy went to Department of Energy, Idaho, who are the regulator.
The thermal point you mentioned is super interesting. So can you generate direct industrial thermal heat from your system if the customer wanted it for that purpose rather than straight electricity?
You could. And then once the customer pays for it, you do whatever they say. But no, in reality, we don't really consider that to be a great use case for a portable microreactor of 1 megawatt. A lot of our customers will be out on the edges, off of the grid, on little microgrids. And in those regions, electricity is pretty expensive to generate. They can't just tap to a grid. And so electricity has a higher value than heat pretty much always, right? So the economics of a microreactor are challenging. So it often would not make sense. Although there's nothing preventing that. We have about a 700 Celsius outlet temperature in the design.
And I guess you're probably talking, 1 to 2 megawatts of thermal heat, which is probably not enough to do a ton of industrial use cases?
3.5 megawatts.
Oh, yeah, you said that. That's right.
Is
Yeah,
what we operate at. I mean, you wouldn't recover 100% of that, but you could potentially. If there were a sufficient number of customers, we would do it. We could sign up for that. But the reason we don't do that today, we're doing mass production. We want to make every single reactor the same. We want to deploy a fleet of hundreds to thousands of reactors out in the world. That's kind of the end market size for us. We don't really want to make more than a few thousand of this reactor design. We think that fills the market sort of perfectly and addresses the most painful areas, right, where you might be operating these. And so we don't want to make a custom unit to make heat, for example, right? Because what I want to do is get up to the point where we're making 50 reactors a year.
And would customers be buying reactors from you directly, or would they be entering power purchase agreements for the power that the reactors generate, but you own the reactors? Like, what's the setup there look like? Or maybe you don't know yet. I don't know.
It's a fun question. I think energy is really interesting, right? Because everyone needs it. If you look at Kaleidos, our product, what it does, it's not just energy that can beat diesel at cost, but it gives you resilience. It can give you heat. It avoids CO2 emissions. It avoids fumes, right? Exhaust fumes. And when you think about energy sales, there's a whole bunch of different ways. If somebody can finance purchase of a unit up front and they want to do that, that may be the case for military-based customer, which is a really great one because they value actually all of those things I mentioned. Then we'll do that. We can directly sell it. There's a Army reactor office that could operate it. Although military-based, sometimes they are their own utility. Sometimes they have a very small utility that operates the base power for them through a contract. Sometimes they have a connection to a grid and they're working with a much, much bigger utility. And so we've seen every single format and we have to be able to sell in all those areas. So there's no simple answer.
Hey everyone, I'm Yin, a partner at MCJ Collective, here to take a quick minute to tell you about our MCJ membership community, which was born out of a collective thirst for peer-to-peer learning and doing that goes beyond just listening to the podcast. We started in 2019 and have grown to thousands of members globally. Each week, we're inspired by people who join with different backgrounds and points of view. What we all share is a deep curiosity to learn and a bias to action around ways to accelerate solutions to climate change. Some awesome initiatives have come out of the community. A number of founding teams have met, several nonprofits have been established, and a bunch of hiring has been done. Many early-stage investments have been made, as well as ongoing events and programming, like monthly Women in Climate meetups, idea jam sessions for early-stage founders, climate book club, art workshops, and more. Whether you've been in the climate space for a while or just embarking on your journey, having a community to support you is important. If you want to learn more, head over to mcjcollective.com and click on the Members tab at the top. Thanks, and enjoy the rest of the show.
You brought up the fuel a couple times. I have some questions about that, but I guess starting first and foremost, for a customer who may be buying a nuclear reactor, there have to be some kind of requirements over their ability to be in proximity to and or managing a nuclear fuel source, I would think. Yeah?
Absolutely. Yeah, that's a NRC commercial operating license. That's the only requirement that there is. So depending on what the customer wants to do, right, someone needs to hold the license and hold the liability for the reactor. That is typically a utility, typically a larger utility, because usually we're looking at 1,000 megawatt reactors. But certainly there could be smaller utilities, some that we found at military bases who don't have a reactor now, who have said that they are comfortable taking on that liability. And so It's another one where every answer is sort of possible. It could be simplified this way. There's two models. One is you've got a nuclear utility. They're happy to go put a reactor in some location and make power with it. Or you've got a small utility that's going to install this basically as if it were a diesel generator. And I think that's the more interesting place because that only really makes sense for a portable micro-reactor. And there are some late 90s regulations that were passed called PURPA that allow cogeneration to be installed on facilities or solar or wind. Basically, these projects that we know improve efficiency, improve the cleanliness of power production. And those regulations allow you to put reactors onto a grid and get favorable prices. And they apply to things that are a few megawatts. So there's actually some interesting work there.
So just to make sure I understand that part correctly, so there's been a lot of attention, and I actually want to talk with you about some of this, about getting a reactor designed through NRC and getting the reactor itself approved to be operated. But it sounds like there's a separate NRC approval process for the organization that ultimately plans to run the reactor, which is that they have to have their own commercial license to manage a reactor themselves.
Yeah, there's a couple pieces to it. There's a quality assurance requirement that basically is an evaluation of the company that would operate it. It was actually added as an appendix to the original Atomic Energy Act. The thing you might typically hear is, we call it today is NQA1, which is actually an ASME standard that is followed. It's a nuclear quality assurance program.
Yep. So you have to go through the process on your own of essentially getting your reactor approved from a fuel test perspective and a safety perspective and all that. But then whoever is ultimately buying it from you also has to obviously hold some kind of NRC license themselves.
That is correct.
And so that would, in my mind, make me think that you're not doing like a direct sale to a hospital or a local NGO doing disaster relief. You're still probably selling to an energy company that is managing this on behalf of those clients, yes?
Yes, I think that is the most likely model for our earliest customers. Although that being said, let me present this case. In the farther future, we need something better. What we need is to have permit parity with diesel generators. So I'm going to use a theoretical town of 1,000 people way up in remote Alaska somewhere. Right? And let's say they have a diesel generator today and they have no solar and no wind because they have weather issues and they don't have a bunch of flat land. All right. And so they're looking at this diesel generator. It's about to be at end of life and they want to go, well, should we get another one of these or should we get a nuclear generator? And if you put in a diesel generator and you operate that for 20 years, it actually leads to about 12.3 avoidable deaths over that time period. That's just the numbers because there's carcinogenic diesel fumes generated. So if you really want to protect public health and safety, which is what all the nuclear regulations are about, you want to get to a point where you've got permit parity, where that theoretical town can go, hey, we really want to have the best, most modern thing that is the safest and the cleanest. And added bonus, you are preventing CO2 emissions. So we are pressing for that slowly and in the background. That's not something that's going to change rapidly at all, right? But maybe this is the 10 years out from now when we have these reactors operating and we've gone through all these rules with the sort of painful permitting rules that are used for a thing that is 1,000 times larger, that make a bunch of assumptions like that there's no internet and cybersecurity rules are not encoded. The thing we're building is not a gigantic building that people fit inside of, which is an assumption in the rules.
It's not, but you're still putting enriched uranium in someone's hands. Ultimately, you have to trust the person running these things, yeah?
Certainly not in their hands, but yeah.
Well, yes, not in their hands, but into their control.
Yeah. I mean, diesel fuel can be used in dangerous ways too. But yeah, there's two kind of sides of this. One track, hey, no one's done a new nuclear reactor in 50 years. What's the reason for that? Well, it's a lot of these questions you've got. It's highly complicated, and there's a lot of things that can go wrong and a lot of roadblocks. And so our company is all about doing all of the work, right, and doing it up front, and then also helping modernize the NRC and developing the best possible solution for the public and for the grid, for companies and for the country.
On the fuel question itself, this is a TRISO fuel, right? And as I understand it, the actual uranium element in there is HALEU, which has some challenges from a supply chain perspective today in that it's mostly enriched and manufactured in Russia. Am I following correctly?
Not mainly there, but Russia certainly has enrichment capability. And that's sort of because of this program in the 90s called the Megatons to Megawatts program, where the U.S. got Russia to agree to reduce the total warhead count. And in doing that, we traded a lot of natural uranium back in exchange, which then led to Russia developing on this enrichment capability and becoming a major supplier in the world. and not just for HALEU, for every form of that enriched material. That left the U.S. with a giant stockpile of high-enriched uranium from weapons that we downblend to get to about a 20% enrichment level, which is where HALEU is. And so we just have a different capability. We don't enrich up, we downblend from weapons grade. And this is a very deep stockpile. But overall, it's a good thing, right? Led to far fewer nuclear weapons in the world. I think the counts are maybe 1/3 of what the peak was.
On the weapon side, yeah. So on the HALEU side, is there a domestic U.S. supply chain of it today?
There is uranium hexafluoride gas that gets enriched in southern Ohio, about 900 kilograms a year, I think is the current capability that the DOE has stood up. They've been working at this for a while. They got to that point. We need to have deconversion added to that. So that uranium hexafluoride gas needs to get turned into an oxide that can then be fabricated into fuel. So I believe an RFP went out very recently for that from the Department of Energy, and there's about $2.7 billion committed to what's called the HALEU Availability Program that was approved. So a lot of stuff's moving in the right direction. A lot of that will be too slow for our purposes. So we're working directly with DOE headquarters on every possible option. And we have a lot of congressional support in this area as well.
It seems like we haven't talked about it yet, but the ADVANCE Act, which just recently passed and was signed into law by President Biden, I think getting a domestic supply chain of HALEU fuel was actually a chunk of that new law and trying to expedite that because many of these new reactor technologies are planning to use it.
Yep, absolutely. That's right. The one positive is our scale, we use about 1/200th of the fuel required by one of the SMRs using HALEU. So that helps with the challenging supply chain.
You just used the phrase SMR, and I want to clarify for folks the difference between what you're building at micro-reactor scale and what an SMR is, because I feel like the term gets used too interchangeably across all small nuclear reactors. So I think of something like a TerraPower or an Oklo or companies like that, which are trying to build essentially gas power plant replacements as nuclear power plants. Those are quote unquote SMRs. Would that be correct? Small modular reactors?
I think if we use any specific company's name and we try to define them, I think we'll be wrong. We won't make them happy.
Okay.
So maybe broadly, though, I think Oklo describes their Aurora plant as a micro-reactor, for example. But the distinction I like to make is I think you're totally right. People say SMR, and I think they mean new nuclear pretty often. They mean like basically, hey, anything smaller. So a normal grid scale is about 1,000 megawatts. An SMR is something usually about 100. Could be a few hundred. There's a pretty big range, but it's about that much smaller. And the idea is fewer buildings, fewer welds, fewer parts, faster construction. And that's good, right? The financing of a big project and the slow construction timelines are a big pain for those 1,000 megawatt plants. If you drop down to the scale of a microgrid, you are actually targeting totally different markets where you could power a microgrid at that scale, and you can be passively safe at those microreactor scales. So not needing to have cooling and backup sources for power for cooling. But we even don't consider ourselves a microreactor. And what we're developing is a portable microreactor. I think we might be very near the top end of the sizes for a portable microreactor. So a megawatt, maybe a few megawatt.
And what does the NRC process on your end look like? I think you're planning to have a fuel test within the next 2 years that the NRC would essentially approve. Is that kind of the next big milestone for you?
So for the NRC path, we're in pre-application right now. There's sort of three main things to do with the NRC. One is we have to build a factory, and we have to go through the approval process for that. That's use something called a manufacturing license. That really only applies for portable microreactors also. All other reactors are going to be constructed on site, and so they will usually get a construction permit. So this is kind of like the portable microreactor version of a construction permit. The other two bits are the site, the actual customer site we're going to go to. So for that, we plan to do an early site permit next year for the first location, then environmental permit, and then the operating license for that customer site. And then there's separately the design certification piece of this, which that can be bundled with the manufacturing license.
And I think most of us who have spent any time here think of these approval processes as being multi-year, incredibly complex structures. For a portable microreactor, is there any streamlining to getting through these approvals?
I don't know if I would call it streamlining. There's definitely special attention being given to microreactors. A lot of that driven by the DOD stepping out and creating the Pele program. They have taken a bunch of action, working with folks at national laboratories And the maybe single best thing out there is that the NRC has released a white paper called Micro-Reactor Licensing Strategies, where they lay out exactly what gray areas there are that they see, and they mention some of the ways they are thinking about addressing all of those. It's all very positive, but it doesn't directly lead to any streamlining. We don't expect there to be any for the very first units, maybe even for the first 10 of our units.
And famously, I think no new designs have yet gone through NRC and successfully come out the other end. It seems like there is an attention for that to change over the next 5 years. If you could predict the future, what do you think it looks like?
So I don't think we can blame the NRC for that. I think it's certainly true, right? No new designs that have been constructed. I think there have been permits, though, right? There have been certifications, but nothing constructed. I think there's been design certifications since the 1970s. So I think the real big problem is it's something outside of that. It's really, if you look at the last 50 years of nuclear in the US, the big problem that we've had is that we don't have the customers staying with the reactor developer. What you see is sort of a cycle of like just a dissatisfied customer. And I think a lot of it was, right, there were a lot of knee-jerk reactions to things like 3 Mile Island and Chernobyl and statewide bans on any new plant that I think killed nuclear in the US pretty directly. But what we really need to do is, as reactor developers, we need a whole lot of reactor developers to succeed. We need them to succeed at every scale we talked about, right? The portable micro-reactor, the micros, the SMRs, and even the grid scale. What we need to do is have customers, and we need to deliver on time and on budget for those customers. Because I think nuclear has failed to do that too often. And even though I think people are more excited about nuclear energy than ever before, because of a focus around climate, because of the 90s and early 2000s where wind and solar really started taking off and becoming a bigger proportion of power on the grid, there's now, I think, a really interesting way to combine solar plus nuclear, and solar and batteries and nuclear. And a lot more people are there. And I think we're not enough championing that cause yet. So that's really it, I think, more than the NRC not being in the way. I don't think there's ever been a case where the customer has been really happy with the developer's progress and their costs, right, and their schedule, and the NRC has blocked a permit from happening. So I think that's how we'll solve it.
Many would say that customer demand right now is, you look at the demand forecasts for energy in the US, and we're turning into a demand upturn for the first time in a couple decades. A lot of that being driven by the electrification of industry, but also a lot of it being driven by sort of data center demand and this, that, and the other. And so you've got these hyperscalers now working with the utilities to understand where their power is going to come from. And thus they're putting pressure on them to look at all sorts of clean energy sources, one of which is nuclear. And so that would result in sort of pressure to build more large plants that can solve these sort of hyperscaler power demand needs. As we've discussed, your customer base is going to be quite different than that. Where is the pressure going to come from to help you guys get through all of this, if that makes sense?
Yeah, well, it's from various places, but there's two bits of this. I've sort of just badly explained so far. So appreciate you asking a different way. We've got essentially remote power, remote prime power. It's some microgrid where it's way too small for anything 10 megawatt even, definitely way too small for something 100 megawatt. All those sort of nearly off the map places, right, which could be just people living there, but it could be that they're doing mining, right? It could be that this is the economy of this like extremely tiny little town. Well, they can also use nuclear energy and they can avoid the emissions associated with other forms. So that is an important demand signal. We have actually a couple of agreements with customers specifically in that area. The other bit is from the military. So there is a need to have a small amount of power that is a critical, resilient core at a military base. And there's both the Air Force and now the Army are coming in as well, sending in that signal. So yeah, it's a totally different scale where some of that's happening. We certainly don't have much to do with a hyperscaler plant where you really want to get super low cost of energy. I'm really glad we're talking about nuclear for that use case, though, because there's no reason that you can't take a nuclear power plant and scale the output power up and down rapidly. If you think about the first nuclear reactors for power in the US, right, these are submarines, actually. And a submarine, you can throttle up and go full steam, and you can do it right away. So because it was designed to do that. Reactors aren't base load power. They just happened to be because that was convenient, and we had a whole bunch of coal and oil being burnt on the grid that we were scaling around. But all the reactor design happened in the 1960s and 70s in the US, all the deployments. And then solar and wind, which they vary because there's a daily output curve there. Those didn't happen until the 90s or 2000s, so it just happened later. And part of this like redesign cycle where people are focusing on SMRs, I think it's going to shock some people who aren't aware and don't realize that you can just throttle out around the output of a reactor. I think TerraPower does that very well, actually, with their design, for example.
Well, great. Doug, thanks for clarifying that and sharing all of that. And maybe share a bit about where you are today from a financing perspective and how you've gotten to where you are in terms of capital.
Yeah, thanks. Okay, so early on, we raised capital really through angels on safes, like when we were very small. We then did a Series A and Series B round. So we've done 2 priced rounds. We've raised $60 million in total. We actually just ticked up over 60 full-time employees. We have this 38,000 square foot building, and we are about to activate our passive cooling demo unit, which is the purpose of the funds that we raised in the Series B, where Andreessen Horowitz are the lead investor. And after we do that, we will move into raising another round, and that round will be the last one before we are able to go critical at full scale at Idaho National Lab.
Amazing. What else should we have covered? What did I not ask about?
There is some pretty exciting stuff happening with the Army now coming in and looking at reactors with help from the Defense Innovation Unit. So there's an interesting proposal coming up pretty soon. I think there's nothing public yet about that, but people might want to be looking for that if they're interested to hear what's happening at the portable micro-reactor scale.
Very cool. I'm glad you've mentioned now the DoD a few times. All of us in the clean energy space probably discount the amount of influence that the DoD can have on driving innovation forward based on purchase interest.
Yeah, it's a super interesting customer. I think they have a lot to do with nuclear, not just portable nuclear either, because some of the biggest military bases are, I think, about 40 megawatts, just the base by itself. And it's always surrounded by a community, like within a city. But they scale all the way down to way out in the middle of nowhere, radar installation that can never turn off. And in those places, we're burning diesel to do that.
Mm-hmm. Well, Doug, thanks for joining us today. Thanks for taking the time to explain what you're building, and can't wait to continue to follow your progress.
All right. Thanks, Cody.
Thanks again for joining us on the My Climate Journey podcast.
At MCJ Collective, we're all about powering collective innovation for climate solutions by breaking down silos and unleashing problem-solving capacity.
If you'd like to learn more about MCJ Collective, visit us at mcjcollective.com. And if you have a guest suggestion, let us know that via Twitter at MCJPod.
For weekly climate op-eds, jobs, community events, and investment announcements from our MCJ Venture Funds, be sure to subscribe to our newsletter on our website.
Thanks, and see you next episode.